Yesterday we discussed over and not, and I have a comment here. I multiplied 10 here, but nobody asked why I multiplied 10. I think all of you are familiar with the Bode plot, where we uh, plot the amplitude of the transfer function. So we have, do you know why I multiplied 10, not 20? In Bode plot, while doing the Bode plot, we multiplied 20, right? So do you know why we multiply 10 here, not 20? If you know, I'll not discuss this.
Twenty represents the slope of the
20 represents the slope.
of the board plot.
You are mixing cause and effect. You are mixing cause and effect. So in Bode plot, we have the amplitude of the open loop transfer function and the phase, right? And then for the amplitude, what we do, we consider 20 log 10 or G. This we plot in a semi-log graph paper, right? Now the question is, here we multiplied 20, here we multiplied 10. So is this wrong, or this you know that that 20 has to be multiplied, but how about this one? Why we multiplied? The question is why we multiplied 10, not 20. Okay, and the answer lies in this. Of which quantity you are taking the logarithm of. In this case, this is amplitude. And what is the unit of the transfer function? Transfer function is unitless, right? So when you take the logarithm of unitless quantity, the unit that you get is simply dv, right? Now in this case, it has unit hertz, and when we are doing the logarithm, we are getting dB hertz. But the difference between these two is that here we are multiplying 10 before logarithm, and here we are multiplying 20. Now we define the signal power, right? So if you recall, in the calculation of average power, we need to do x squared of t, right? And then that has to be integrated. So the answer lies in this x square. What is the relationship between power and amplitude? So to get the power, we need to square the amplitude, right? Now here we are actually taking the logarithm of the power. So if you want to express this in amplitude, you need to actually do amplitude square. So if you do amplitude square, then 2 in the exponent will come out because we are taking logarithm. So 2 will come out and you get 20. This is why in the logarithm of the power, we multiply 10. And then when we are doing the same for amplitude, we multiply 20. Okay? Yesterday I told you that we will look at a simple example after deriving 3 estimators, but I think it is better to do the problem as and when we derive an estimator. So yesterday we derived the MMSE estimator. So let's solve the problem for the MMSE estimator. It goes like this. Suppose x is a constant. It is related to its measurements y as y is equal to x plus b. Where b is Gaussian noise, assume that it is known a priori. A priori means before measurements are made. Okay, so prior information, basically it is called, in estimation theory, it is called a priori. Assume that it is known a priori that x takes on a value from Gaussian distribution uh, of 0 mean and variance 4. Noise V is distributed as, so the prior information is given about X, that it is Gaussian distributed with 0 mean and variance 4. Noise V is distributed as this, so it has 0 mean and variance 1. Note that the second argument of N denotes variance. Multiple measurements of Y are given as, so we make different measurements of Y for the same constant. X is a constant. X does not change with time. X is a constant. Multiple measurements of Y are given as this. So we have 1, 2, 3, 4, 5 measurements of Y for constant. Design a suitable estimator and estimate X. Justify why you have selected the estimator. Now, these types of questions are asked in exams. There you have to do this for a particular estimator, and you also need to justify why you have chosen that estimator over others. Okay, now here we are going to do this for all the estimators that will derive. The first one derive or derived. The first one is the MMSE estimator. So let me. So he is Gaussian x, okay, 0401, and then we have this 2.39. We have y is equal to x plus b, and then prior information tells that x is Gaussian distributed with 0 mean and variance 4, and then b is again Gaussian distributed with 0 mean and variance 1. And then we have been given different values of y, 0.39, 2.39, 2.29, 4.14, 2.09. So these are the 5 different values of y, and we need to design an MMSE estimate. Can you tell me quickly how you will go about it? What will you do? You don't know how to solve this problem? We did not discuss these types of problem in the class. We discussed or did not discuss? We discussed or did not discuss if y just you say a single y is given. Tell me what you will do if single y is given, just only one y. In that case, how we can solve this problem? This is discussed in the class or not? If you do not respond, then I see no point in discussing further. So either you are not following anything, I am not able to understand what the problem is. All the expressions were derived. Examples were also discussed. Something similar is being asked, you are not able to respond. What is the reason? I'm asking a simple question, is a problem similar to this one was discussed in the class? Yes or no can be at least said, right? So this type of problem was not discussed in the class. Should I interpret that? Should I interpret that this type of problem was not discussed in the class? I want your response, otherwise I don't see any point in proceeding further. So nobody wants to respond. So you are not getting anything at all that is being discussed or explained, right? What should I interpret? What is this? Nobody is responding. What does it imply? You are not following what I am saying in the class? Shall we drop this topic altogether? Because you are not following anything, right?
Ma'am, Siri ma'am.
Yes.
Ma'am, theory part of MMSA is covered in the class. But
Before that, didn't we discuss a problem? What did we say about that problem? Did you discuss a simple problem in the class? Yes or no? And yesterday I repeatedly referred to that problem while discussing MMSC. Do you take class notes or not? Don't you have your own notes? Can't you go back to your previous notes? Okay, answer this question. Did we discuss a problem? Forget about MMSE or anything. Did we discuss a problem last week? Yes or no?
Yes, ma'am.
So what did we talk about that problem? Can we relate that problem to MMSE? Did we refer to MMSE while talking about that problem? Yes or no? We did not refer to MMSE. While solving that problem, we did not refer to MMSE, right? Okay, tell me whether you take class notes or not. If you do not take class notes, at least you have some material in front of you, or you can easily access the class material. Can you look at the class material quickly and tell me what we discussed last Friday in the context of that problem? And yesterday when I repeatedly referred to that problem, nobody said anything. And today you are just quiet, not responding at all. What does it imply? If there is a problem, you are not following anything, then you should tell me, right? If I ask simple question also, you are just not able to answer anything. Apur, what is happening?
Now I have to read this topic once more.
At least you attended the class, right?
Yes, ma'am.
Last class, the last Friday, did we discuss a problem? Did we refer to MMSE in the context of that problem?
Yes, ma'am.
So is this problem similar to that one? Can you look at that problem, all of you? Can you look at that problem and tell me whether this problem is similar to that one? Because I cannot do everything from scratch. Look at that problem quickly and tell me, all of you. And if there is something wrong, you are not following something, you should tell me. I do not want to keep going this way and you are not following anything. Okay, there is no point in going this way. You already discussed a problem, and if I ask you anything about that, you are just not able to say even a single thing. That just requires looking at the problem we discussed in the class and this one. Only this much is required. Simply attending class will not give class any marks because that class participation marks will be multiplied. as a scale factor. So tell me at least whether you can do something by looking at that problem. What was that problem? Are they similar? The problem that I told you just now, is this one has some similarity with the problem that we discussed last Friday? At least you can refer to last Friday's class notes, right? If you have not taken any notes on your notebook, at least you can go to your class materials folder and look at it. Or you don't even download that. The night before the exam, you will download all the class material. This way, you will not be able to answer a single question for this exam. Tell me that question, at least that one, if there is any similarity or not. Otherwise, what is the point? Now, if you do not have access to class materials, if you cannot look at that, lend me that also. At least I'll get to know that you cannot do anything other than just listening. Because this way, I don't think there is any point in proceeding further. You are not getting anything. If I ask simple question in the class also, you are not getting anything. So, shall we drop this topic altogether? It looks like you are not getting anything in the class. Just tell me frankly, I do not want to keep going this way. If you are not getting something, if it is completely abstract to you, then that also you can tell me. I'm telling you, tell me. Just feel free to tell me the issues. Last Friday's class notes also you cannot access. Should I conclude that you have no access to any class materials?
No, ma'am.
No, ma'am. You cannot access that.
No, ma'am. Yes, ma'am. Yes, ma'am. I can access.
So if you can access, then why don't you go there and look at the problem that we discussed in the class and tell me how it is similar to the one that we have just now considered.
Yeah, ma'am. It is similar to that. And y is equal to s plus n.
So what are the solutions given?
That is f of y is similar to Gaussian.
Similar to Gaussian.
Sorry. Summation of this mean and variance.
Summation of mean and variance. I don't understand what you are saying. Did you discuss a solution to the unknown quantity? Yes or no? And this is a question open to all. So don't think that I am asking only Shujit. So I am asking you to refer to the problem that we discussed in the class last Friday and tell me what solution we discussed in that problem. What was the solution to S?
And we have to find conditional mean, conditional variance.
So which one will you take as a solution to S? Mean or variance? Which one could be the solution? You tell me if you are given mean and variance, which one will you take as the solution? Tell me that. You understand that or you do not even understand that? I mentioned in the class which one should be taken as the solution. You understand that or not? Do I mean, I should conclude that you are not following anything at all. I'm just simply saying something. Should I conclude that? If you do not respond, I'll conclude that only. So whatever I discussed so far, you are basically not getting anything. So if I tell you that this random variable has this mean and this variance, which one will you pick as an estimate? Mean or variance?
Mean, ma'am.
Mean you should take as the estimate.
Yes, ma'am.
So what is the
Yes, ma'am.
estimate for that problem? For that problem, which one is the estimate? The problem that we discussed last Friday, which one is the estimate? Which one is the estimate? Just now you said mean, so which one will you pick as the estimate for the problem we considered last Friday?
F of S, ma'am.
F of S you will take as an estimate of S.
No. S given Y.
Just now you give the answer. And just need to go by that in that context. So which one is the estimate of S in that problem? Our objective was to estimate S. So you did not understand the parameter which we should take as the estimate of S in that problem. That problem was discussed last Friday.
We took estimate of S as the prior given distribution of S.
So that was in the beginning. Then we need to incorporate the measurements. Using measurements we did something. At the end what we considered as the estimate of S. Which one will you consider as the estimate of S? Which one do you think is most likely estimate? What did we find in that problem? Tell me first what we found in that problem. We did so many things, right?
We found
Ultimately,
mean and variance for f. We found f of s given y, and then we found the mean for s given y and variance also, mu and sigma square.
okay, so which one of them should be the estimate of S? Given mean and variance, which one should be the estimate of S?
It should be the
Ma'am,
Okay, Ajita,
mean.
you think it's mean? Okay.
I think
Krishna,
it's
what is? Krishna, what you are saying?
ma'am, it should be conditional mean s given y.
Hmm? Yes. And is not something written related to MMSC in the class note? That later we'll see that this is the MMSC estimate.
Yes, ma'am.
yes, ma'am. We found x given y estimate as e of x given y.
Yes. So this is the estimate. This is the conditional mean. This is the expression of conditional mean. And this is also minimum mean square error estimate. Yesterday we proved in the class that the conditional mean is the minimum mean square error estimate, right? So we need to follow that approach and find the conditional mean. The conditional mean here is given x given y. And it is y by sigma v square plus x bar by c by x square. And then we have the conditional variance. So this is the MMSC estimate. This is MMSC estimate. Now, what do we know? Do we know y? Yes, if we take one y, we know this. So with the first y, now this has to be done sequentially using one measurement at a time. First y will be put here. For the first y, x bar is 0 that we are getting from the prior distribution. X bar is 0. Sigma b square we know it's 1. Sigma b square is 1. Sigma x square is also known, it is 4. So we know everything that we need to know. So this will be the first y. X bar we know, sigma b square we know, sigma x square we know, and this also we know. So we can find this one, and that we have to put here. Then everything we know, so we get this one. So from all this we get the first estimate. Which is mu x given y, and we also get the conditional variance. For the second y, instead of taking x bar is equal to 0, since we have a better estimate of x, we will use that one. So x bar will be equal to mu x given y, and sigma x square. Sigma x square will no longer be 4. We have a better knowledge of the variance. We will use the previously calculated conditional variance and repeat the same thing. So for the second iteration, instead of taking first y, you will have to take the second y and then do this. So this will be the prior guess or prior information about x for the second iteration, and then you repeat it. You will get new conditional mean and conditional variance. The newly calculated conditional mean and variance will be used for the third iteration. So this way you need to process one measurement at a time. Now here we cannot do the numerical computation due to lack of time. You need to do this. Okay, you need to do the numerical calculation and find the estimate. Okay, so do this. Any question? The next estimator that we will consider in the class is the weighted least squares. Now we consider the following measurement model. Instead of handling a single quantity, now we are actually working on vectors. Okay, so y is a vector, x is also a vector, n is also a vector. So y is the measurement. Let's say we have m cross 1 measurements. Okay, this is put as a vector. Then x, let's say of dimension n cross 1, and then n has to be m cross 1. So this is the measurement model. Now we have a nonlinear function h. It's not necessary that y has to be a linear function of x. Y can be a nonlinear function of x also. In most of the cases, as far as navigation is concerned, y is a nonlinear function of x. Okay? Uh, now we cannot find an estimate using the nonlinear function. We need to linearize the nonlinear function. So for that we require some guess. So let's say we have some guess of x. X is unknown, y is measured, and n is the noise, measurement error that gets added while making measurements. And n is statistically modeled. So let's say n is Gaussian distributed with zero mean. Generally the measurement error will have zero mean. Okay, zero mean, and let's say the covariance is W. Now instead of writing variance, we are writing covariance. We discussed covariance. So in case you are not sure what covariance is, refer to it. Is the covariance. We also talked about the Gaussian PDF for an n-dimensional random vector. So W is the covariance matrix. Okay, it is symmetric. And it's not necessary for the derivation that W is diagonal. W can be any matrix, symmetric, positive definite matrix. Okay, but generally W is diagonal. Generally, but for the derivation of the estimator, it's not necessary that W has to be diagonal. Okay, now we assume some guess for x. So let's say x hat is the guess of x. Okay. Now we assume that it is an unbiased case, meaning E of x hat is actually E of x. Okay. What is the error? Error is x minus x hat. We are interested in this delta x. We do not know x. We have some guess of x. Okay. So we are interested in the difference. If we can find the difference, then by adding that to the prior guess, we get the estimate. So our objective is basically to estimate delta x. Okay. And the expectation of delta x is 0 because we know that E of x hat is equal to E of x. Now we also have some information about the variance or the covariance, although later we'll see that this is not required. So let's call this P for derivation purposes. Okay, this is P. And since x and n are completely independent processes, they are independent. X and n are independent. Okay. Since we have some guess of x and we cannot directly handle nonlinearity, we need to linearize it. We'll first linearize the nonlinear equations using the guess. Okay, and we are going to find the estimate using the linearized version of the nonlinear equations. So using the Taylor series expansion, we can easily linearize the nonlinear equations. Then we have delta y is equal to capital H delta x plus L. What is capital H? Now we had a function h, right? And h is actually mapping this n cross 1 vector to m cross 1 vector, which means h is actually a set of functions. So we basically have n functions, okay, which m functions which take n arguments, okay. We basically have in H we have actually a set of functions h1, h2 up to hn. So we have m functions. So let's put a bar here also. How do we find capital H? Since we are doing Taylor series expansion, if we go by the definition, we have n columns because x is of dimension n. And we have m rows. So this is capital H. Capital H is called the Jacobian of H. So with the help of the Taylor series expansion, we got a linearized model of the nonlinear measurement questions. And we are actually interested in finding delta x. As before, we want a cost function to be minimized to find delta x. So to minimize this cost function, we have to take help of this measurement model. First, we need to formulate the cost function. And for that, we need to take help of the measurement model. Now, we want to find an estimate of delta x in such a way that the difference between delta y and h times delta x, this one, is minimized magnitude wise. We are not interested in the sign. Okay, we are actually interested in reducing the magnitude. Now, to eliminate the sign, we need to square. Now, since we are using vectors now, we simply cannot square because this is a vector, right? So we simply cannot square that. So we have to take transpose of this difference and then multiply that transpose with the difference itself. Okay, and that we can take as our cost function. But we want to do something more. Simply by minimizing the difference is not sufficient for us. We want to take help of something more. And that extra information comes from W. So in between we multiply W inverse. How does it help? See, we have this difference delta y minus h times delta x. Our objective is to minimize this difference because we know that we have this measurement model, right? But we also have some noise. It's not that delta y is exactly equal to h times delta x. We also have some noise, right? N, right? N also contributes to the difference, right? Now, whether n is small or large, that is statistically determined by its covariance matrix. Generally, W is a diagonal matrix. So, if a particular diagonal element of W is large, n is n by O. So, here we have written the dimension m cross 1, right? So W is M cross M. W is the covariance matrix, it is M cross M. Right? And let's assume that it's a diagonal matrix. For derivation purposes, we don't have to impose that constant, but for generally W is a diagonal matrix. So for understanding purposes, let's assume that W is a diagonal matrix. And the second element of W is very large compared to other elements. What does it imply? Now, if the second element of W is very large, it implies that the second element of N is also likely to have a large variation, because the diagonal elements actually show the variances of the individual elements of N. So variance is large means it has a large spread, and the particular element, the second element of this N vector, will have a large variation, large spread. So it's likely that it will take a large value. So this implies that the second measurement element will have a large N, large noise. And that is what the W matrix tells us statistically. So we do not want to rely heavily on some measurement which has large N, large noise. And the best way to give more importance to good quality measurements with low N is to multiply W inverse. If a diagonal element of W is large, its inverse will be small. So if its inverse is small, that means we are giving more importance to that particular measurement. If the inverse, if the diagonal element is small, that means we have good quality measurements and its inverse will be large, correct? If inverse large means we are giving more importance to that particular element. And the reverse happens when the measurement quality is not good. If a particular diagonal element is large, its inverse is small, and therefore we give less importance to that particular measurement. And that information is automatically incorporated by this W inverse. Now, since we are multiplying W inverse in between, it is called weighted least squares. If we had not multiplied W inverse, then it would have been simple least squares. Now, when we deal with the scalar quantities, we just square. Since here we have vector quantities, we need to take transpose and multiply with the difference. But it's nothing but least squares without W inverse in between. The moment we multiply W inverse in between, we are actually weighting the difference. That's why the name is weighted least squares. So this way we are incorporating additional information. We are telling the estimator that this measurement has good quality, so give more importance to this measurement. This measurement has bad quality, so do not give much importance to this measurement. And that information is statistically incorporated in the W matrix. If W is large, measurement quality is bad, W inverse is small, and therefore relatively less importance is given to that particular element. So this is the cost function which we want to minimize. And find an estimate of delta x. Now, what is the dimension of this one? It is 1 cross m. This is m cross m, and this is m cross 1. So this is basically a scalar quantity. Cost function is a scalar quantity. Although we are dealing with vectors, the cost function is not a vector, it is a scalar quantity. Now to find the derivative, we are interested in finding an estimate of delta x. such that the derivative is equal to 0. And to find the derivative, we will make use of this identity. Let's say we want to find the derivative of A transpose B. A is a vector, B is also a vector. Okay, so this one actually is given like this. Notice this one carefully. We have done B transpose A. Here A transpose B as it is, but for the second term we have done B transpose A. Okay, the same thing here we are going to apply. So let's call this A transpose and this one is B. Okay. So del J del delta X. Here let's put X. So first we have del A transpose by del X. So in place of del X we have to write del delta X. Right? So this we have already considered as A transpose. The first term we have already considered as A transpose. We need to consider only those portions which have delta X. So this term has delta X, this also has delta X. But W is not a function of delta X. Delta Y also explicitly do not have delta X. Okay. So what will be the derivative? Let's consider the second term. So at least tell me for the second term what the derivative is. You can tell for the first term also. Tell me for the first term what the derivative is. What is the derivative of delta A transpose by delta X? Del delta X. What will be the derivative? Hmm? So if you take the transpose inside, you have delta Y transpose, and this one will be what? Delta Y transpose. What is the transpose of the second term? X delta X. What is the transpose?
Delta X transpose into S transpose.
So if you take the derivative, which term will come? H transpose will come. W inverse will come. And then B also you need to put. Right? How about the second term? What will happen to the second term? You have to do B transpose. So B transpose means you get the same thing as before. H transpose. How about A? What is A? So for the derivative part you are getting H transpose because you need to transpose this one, right? The second term you need to transpose this, And again you have delta y transpose, delta x transpose, h transpose. So you just take h transpose because you are taking derivative with respect to delta x. How about a? What is a? Tell me what is a?
W inverse transpose.
W inverse transpose is what? W is a symmetric matrix. W
W.
is W inverse, just W inverse. And here we already have transpose, so it will just be this, right? And for the estimate of delta x, let's call it delta x hat, this will be equal to 0. Now we just need to separate the terms and arrange them properly. So we'll group all the delta x hat terms together. So basically both are the same, right? So what we have is, if we rearrange all the terms, we basically have this H transpose W inverse H delta x hat is equal to H transpose W inverse delta y. This. Right, now we want to find an estimate of this. How about this matrix? See, H is, let me write next page. So we have H transpose W inverse H times delta x, and then H transpose W inverse delta y. So what is the dimension of this one? We know H is m cross n. So we are taking H transpose, so that will give us n cross n, n cross n. W is m cross m, and H is again m cross n. So we are basically getting an n cross n matrix. So this is a square matrix, okay? And generally, number of measurements is more than the number of quantities, unknown quantities, okay? The dimension. So x you can call the state vector. So the dimension of the state vector is generally smaller. It has to be smaller. Can be equal also than the number of measurements. Okay. So when this happens and H is of full rank, H has full rank, H is a rectangular matrix. H is not a square matrix in this case. We assume that M is more than N. Okay. So when H has full rank, it means since N is less than M, the rank of H has to be N. Okay. When this is satisfied, we have the inverse of this matrix, n cross n matrix. Okay, and then we can find. So don't think that H transpose W inverse H always has an inverse. No, it does not. M has to be greater than or equal to N, and H should be full rank. Otherwise, you do not. And it is also called the pseudo inverse of H. H is a rectangular matrix. We cannot find the inverse of H. So this is the estimate of delta x that we are looking for. Now we already have the prior guess, so we know that x, so let's call this x tilde. This is the estimate of x, and it is given as, this is the prior guess. So x tilde is the estimate. X tilde is the WLS estimate of x. Since we are dealing with nonlinear equations, we had to linearize it, and then we found the estimate. Okay, x tilde is called the WLS estimate of x. Now, if you notice the expression of this one carefully, you will see that this delta x hat is actually a linear function of delta y or y. So in place of delta y, we can always write y, right? We know that delta y is equal to y minus h of x hat. This is delta y. So delta x hat is a linear function of delta y. And therefore x tilde is also a linear function of y. Which is not necessarily the case for an MMSE estimate. In case of MMSE, we cannot guarantee that the estimate will always be a linear function of y. The example that we considered is a very simple one. Okay, for that it's a linear function, but that is not necessarily the case always. Whereas in case of WLS, we get a linear function of y as the estimate. Okay. Now, in case of any estimator, we would be interested in finding the quality of estimate. So, how do we find the quality of estimate? One is the estimation error. Now, we do not know the estimation error, right? Because we do not know the truth. But we need to somehow do something to find the quality of estimate. Statistically only we can say something about the quality of the estimate. So what is the estimation error? In this case, this is the estimate, final estimate. The estimation error is x minus x tilde. This is the estimation error, right? And we want an unbiased estimator, right? So we want the estimation mean of the estimation error to be 0. So is this an unbiased estimator? WLS is WLS an unbiased estimator? Let's find it out. Now, for this we have to use this information about the prior guess. So let's substitute for x tilde. X tilde is x hat plus delta x hat, right? Now x minus x hat is delta x, you know, this will be negative. So we basically have this one. Okay? So this is the estimation error. Now how about this one? We already found that this is mean of that is 0. Here we showed that mean of this is 0. So the mean of epsilon is the mean of delta x and the mean of delta x hat. So you know that this is 0. How about this one? So mean of this one, mean of delta x hat. See the first term, this one, this H transpose W inverse H transpose whole inverse H transpose W inverse. This is not random because H is deterministic matrix, W is the covariance, W is not random. So the first term is not random. So when you take the expectation of delta x hat, the expectation operator only operates on a random quantity. So the expectation of delta x hat has to be, the expectation of delta x hat is this one. How about the expectation of delta y? We know delta y is this, right? So let me write separately. Before doing this, let's I'm sorry. You already got the expression of delta y. Okay. This one, we will make use of this equation. Okay, here. So delta y, expectation of delta y is basically the expectation of h times expectation of delta x and then expectation of n. We already know that n is 0 mean. N is 0 mean, right? So it's basically expectation of delta y is basically h times expectation of delta x. And we already know that expectation of delta x is 0. So this is 0. And if this is 0, then this is also 0. So basically you have 0. The mean of the estimation error is 0, which implies that this is an unbiased estimator. Okay? The second metric that we can use to find the quality of estimate is the estimation error variance if it is a single quantity, scalar term, or estimation error covariance. Estimation error covariance. Because we can only predict it in a statistical sense. We have no information about truth. We do not know truth. If we had known the truth, we would not have taken so much pain to do the estimation. We do not know the truth. Since we do not know the truth, we can only predict in a statistical sense something about the quality of estimate. First, we need to see whether we have an unbiased estimate or not, and then we need to find the estimation error covariance, and seeing the values of the estimation error covariance for a particular problem, we can say, okay, the quality of estimate is good. Or if the estimation error covariance is large, then the quality of estimate is not so good. Okay. So let's find the estimation error covariance. We know that the estimation error, the mean of the estimation error is 0. Correct? So estimation error covariance is given by this one. So for using this expression, we can write the estimation error covariance as delta x minus delta x hat okay. And we just need to do the multiplication inside and then apply the expectation operator on each of the terms. We get 4 terms. So we already know what this is. This one P. It's not necessary that we need to know P, but let's write it as P. The next is this one, right? For that we need to use the expression of delta x hat. Now it's inconvenient to write this big expression every time, so instead let's use this. So let's call this entire thing C, and then we have delta y. So here C is constant, so C will come out. We just need to do this one. Now what is this? We are interested in this one, delta y, delta x transpose. So let's multiply delta x transpose. And then apply the expectation. So we already know this one, right? And how about this one? What can you say about this? The second term? Can you say anything about the second term? Delta x and n are independent, so this is 0. What is C? We know C. And then in place of expectation of this, we can just write this one, HP. We have H transpose W inverse, H inverse, and this one, the matrix itself is multiplied with its inverse. So we basically have P. So I'm just removing the entire thing. All right. Do you understand why I removed the entire thing? I'm just writing P. Yes or no? Tell me quickly. Do you understand why I removed the entire thing and wrote P?
Yes, ma'am.
Then next we have this one, right? Here we found that this is P and this is just the inverse of that, right? Because we have delta X transpose here, delta X hat transpose. So we just have in the argument, we just have the transpose of the entire thing. And P is a covariance matrix. Any covariance matrix has to be symmetric. If you go by the definition of a covariance matrix, it is a symmetric matrix. So here also we are getting P. Next, we are left with the let's see. Here I have written this one. This is class. And this one is written to explain things. We get 4 times. So we have this one, then delta x hat, delta x transpose, then we have delta x times delta x hat transpose, and then we have delta x hat transpose. 4 times. Okay. Just to explain that this will be P, I wrote that intermediate time, but that is not related to the expression. So we are left with only this one, the last one. What is the last one? Here we have expectation of delta x hat transpose. We have to use the expression of delta x hat. Instead of writing the full expression, I am writing C. So this is Cy and then delta y transpose C transpose. As I told you earlier, expectation operator does not operate on any constant term, so we will take C and C transpose outside, and here we have just delta y transpose. How can we find this one? Again, to find this one, we have to take help of this equation. So delta y transpose. Here, see, when we multiply delta y with delta y transpose and use this model, we have 2 terms on the right side, right? So if you multiply, we get 4 terms, correct? So one will be delta x transpose, The other one will be and then here we have H transpose, and then we have H delta X N transpose, then H uh, we're just multiplying and applying the expectation operator, nothing great about it. So we have N delta X transpose H transpose, and then we have N transpose. Now notice carefully, this one, if we are, now let's write the expectation of this. Here also we have expectation. Second term is 0 from here. From here we can say that the second term is 0. Similarly, the third term is also 0. How about the first and fourth term? Tell me quickly what the first and fourth terms will be, and then we'll take a break. How about the first and fourth terms? Do you know the first and fourth term?
Yes, ma'am.
What are they?
In first term, P will be there, and in fourth term, W will be there.
Okay. Now we need to use that here. To simplify this, we have to use the expression of C. C transpose. C transpose means we need to take the transpose of the first term. So W is a symmetric matrix. H transpose W inverse H is again a symmetric matrix. Now just need to do this matrix multiplication. Just see this one multiplied with this one. So H transpose W inverse H, this will cancel out, right? And then on the right side you see we have again, so we have again P, and then H transpose W inverse H, H transpose W inverse H whole inverse. So that will cancel, we just have P, right? Okay. Now let's consider the second term. Here we have H transpose W inverse this whole thing, then W inverse times W. W inverse times W will be identity, right? And then on the right side we have again W inverse H. So H transpose W inverse H, and that has its inverse on the left, right? So if you do all the simplification, you will just have this term. H transpose W inverse H. I am not doing anything difficult. I am just doing the matrix multiplication for each of the terms and then cancelling out terms which are not required. So we got the final expression as this one, P plus H transpose W inverse H whole inverse. So let's substitute this in the previous expression here. So we have P plus H transpose W inverse H whole inverse. Now this C, P will cancel out. We do not have any P in the final expression. H transpose W inverse H whole inverse. This is why I said that we do not need to know P. So estimation error covariance solely depends on the measurement model, linearized measurement model matrix, and W, the covariance of N, the measurement noise. So it does not incorporate any prior information. And this is an inherent drawback of the WLS weighted least square system. It does not incorporate the prior information. We may have some important prior knowledge about the quantity we want to estimate, but the WLS estimator does not give any importance to our prior knowledge. It solely depends on measurements. If measurement quality is bad, it will just give you a bad estimate. But the upside is that it is a linear function of R. Okay? Now for the problem that we considered, y is equal to x plus b. And we had 5 different values of y. I'll show you the method. You need to do the numerical calculation and find the final answer. So we have 5 different values of y. We have been given v. So in this particular case, we need to find w, right? We need to find h, and we have been given 5 measurements. Right, and this is a linear problem. We do not need to linearize anything because we have a linear equation here. And we know that V is, so this sign does not mean similar. It shows that V is distributed as this. The WLS estimator does not give any importance to prior knowledge, so whatever prior information is given in that problem is not useful, and that gives you a hint that WLS is not the best estimator for that problem because you will not utilize the prior information. So V is Gaussian distributed with 0 mean and variance 1. Y has 5 values. So we need to stack all the values and that will give us the y vector. So all 5 values you need to stack one after another, y1, y2 up to 5. You need to stack, and you also need the corresponding v. V will be a vector and it has 5 elements. Okay, so it will have 5 elements, v1 up to v5. How are the corresponding covariance? See, each of these elements will have variance 1. So the corresponding covariance matrix is basically an identity matrix of size 5. It's a 5 by 5 identity matrix. I wrote VIE for identity, that's the comment, MATLAB comment for the identity matrix. What else do we need to know? We need to find H, right? H is the only thing that we need to know. Now for that we have to take help of the equation that is given. So we have 5 values stacked here. Now x is given as a constant. So all of them will have the same x. X does not change, right? So we have basically 5 ones. This is how we need to formulate the measurement model using all the 5 measurements. So this becomes the H matrix. So this is the H matrix which you need to use in the expressions. W also we found, H also we found, P we do not require. So the only thing that you need to do here is to find the suitable matrices, and then you can use the expression, right? You already derived the expression of delta X. Delta X. You can also take the initial guess X hat as 0. Take it 0, you don't know anything about it. The prior information also tells that 0, correct? 0 mean. So you take X hat as 0. Then X tilde will be just H transpose W inverse H whole inverse H transpose W inverse delta Y. Since X hat is 0, delta Y is nothing but Y. This is nothing but Y. Because Y hat will also be 0. X is 0 means Y will also be 0. So this is how you can find the estimate of X. So you know H, you know W, you know Y. Y is given. This is Y. This is only Y. Correct? W is identity. Identity matrix. So you know everything, and then you can also find the estimation error covariance. That's it. So it's 12:43. Do you want a 5-minute break or we'll just continue? What do you want? I'll go by what you want. At least tell me whether you want a 5-minute break or not. If you want a break now, I'll give you a break, but we will be done in another 15 minutes or so. So if you want a break, it's fine. If you do not want, you can continue. So let me know quickly what you want.
Continue, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay, so we looked at the WLS estimator derivation. We also considered a simple problem to know how we need to formulate all the matrices to find the estimate. Now, we could not do the numerical computation because that's just a mechanical thing, but you need to do it. You need to do it for all the estimators that we are considering in this class, and then finally compare all the estimates. Okay, that is something you need to do. And tell me. Now, we have seen that the MMSE gives importance to both prior information and measurements. But it does not guarantee that the estimate is a linear function of Y. We want a linear function because then actually if you have a linear function, then it can be shown that if you start with Gaussian distribution, you can have a Gaussian distribution at the end also. But if it is not a linear function, you cannot guarantee that you will have a Gaussian distribution at the end also. And by you having a nonlinear function, there is a higher chance that the errors will be more. So we do not want a nonlinear function of Y. Okay. But at the same time, we also want to give importance to both prior information and measurements. On the other hand, WLS gives a linear function of Y as the estimate, but it does not take into account the prior information, right? So can we do something which has a linear function of Y, gives a linear function of Y as the estimate, at the same time gives importance to both prior information and measurements? And the solution to that is the linear MMSE. Linear minimum mean square error estimate. So as the name suggests, it is linear, meaning the estimate is a linear function of the measurements. At the same time, it also applies some important properties of MMS. What is that? The property that we apply to derive the linear MMS estimator is called the orthogonality property, or orthogonality principle. So what is the significance of this orthogonality principle? Let me state it and then tell you the significance. So it tells that the estimation error is orthogonal to any function of measurement. This is the estimation error. X hat is the estimate of x. And this is a function of y. Y is the measurement vector. So it tells that the estimation error is orthogonal to any functions of y. So why is it important? Now let's compare this with the deterministic case. We know that for two vectors x and y, this is the x transpose y, and if x and y are orthogonal, then this is 0, right? It says that x and y are orthogonal. This also implies that if we take a projection of x along y or projection of y along x, we get nothing. So there is no component of x along y, correct? Given x, we cannot say anything about y, right? Now when we say that the estimation error is orthogonal in a statistical sense, it says that the error, the residual part, has nothing from y. In other words, the estimate which we want to be a function of y has everything possible extracted from the measurements. You just think of the deterministic case, because here we are doing everything in a statistical sense. Okay, you just draw the analogy with the deterministic case. When x and y, two vectors, are orthogonal, it means that x has no projection along y. Similarly, when we say that the estimation error is orthogonal to functions of measurements, it implies that we have extracted all the information. We have extracted all information from y to find the estimate. That's why the residual part, x minus x hat, this is the residual part, remaining part. It has nothing from y. It's completely different from y. So this implies that we have found the estimate which is the best possible estimate from based on the measurements. Now, this is the orthogonality principle states. But is the MMSE estimator follow the orthogonality? Does the MMSE estimator follow the orthogonality principle? Let's see. Because we did not talk about the orthogonality principle in the context of MMSE. So whatever we discussed, that does not guarantee that the MMSE estimator follows the orthogonality principle. So let's start with this orthogonality principle and show that the estimate x hat is actually the minimum mean square error estimate, meaning the conditional mean of x given y. So let's separate the two terms. We are now dealing with vectors. That's why I have put a bar underneath. I'll put this on the left side, and then on the right side I'll put this one. So I have separated the two terms, and one is on the left side, the other one on the right side. Okay. Now, since we have applied the expectation operator, we need to do integration. We know that x hat is a function of y. So here the only random variable we need to consider is y. And this is a multi-dimensional integration. Although I am putting just one sign. Y is a vector. How about the right hand side? Now right hand side we have two random variables x and y, right? So we need to consider the joint PDF. Again multi-dimensional integration. But here we need to consider the joint PDF. Now we can write the joint PDF in terms of the conditional PDF. Since we have two integration variables, we'll just put the double integration sign. And the conditional expectation of x, conditional PDF of x given y. Dx. This is for the inner integration, and for the outer integration we have fy dy. Now just compare the two expressions. Here also we have f of y dy, here also we have f of y dy for the outer integration. And this condition holds for any y. We did not apply any specific constraint on y. We just took any y, right? So this has to be true for any y, correct? And I missed that g. This is g. G. Okay, I'm just writing here g. So you just see g of y transpose f of y is there on the left side. Similarly, on the right side also we have the same thing. And they are always equal for any y. This condition holds. Therefore, x hat must be equal to the inner integration. And what is this one? Can you tell me what is the right side? Equal to?
Conditional mean.
Yes, this is conditional. And we derive that the MMSE is the conditional mean, correct? So from this we can say that MMSE estimator satisfies the orthogonality principle. Okay. Next, our objective is to have a linear MMSE estimate. And to be generic, we want to process a number of measurements. So we want to derive a linear MMSE estimate with a batch of measurements. Okay. Now, since we are processing a batch of measurements, this is also called a batch estimator. So let's consider the previous model. Uh, so let's say this is m cross 1, this is m cross 1, and this is also m cross 1. This is one measurement. This is measurement 1. Then similarly we'll have measurement 2. Like that, let's say we have capital N measurements. And we stack all the measurements here. We'll not use different notations because these are standard notations, so let's use them only. But the dimensions will be different. Since we are stacking n such measurements, we have different dimensions. So earlier we just had m cross 1, now since we are stacking n measurements, capital N measurements, we have capital N m cross 1. For this particular one, now if x is a constant, we can keep the same x, just like the WLS problem, x was a constant and for all the measurements we use the same x. But that may not be the case always. So let's assume that x is also changing and we consider all the x vectors. So we have for x we have capital N, and then for n we have again capital N